There are only a few things I really love in computer science, and apart from Rust, the first thing that comes to mind is RISC-V. I mean, I already did a whole talk on why RISC-V is so awesome. I wrote 2/3 of the German Wikipedia article on RISC-V. I own microcontrollers and a Framework 13 development mainboard for the sole reason of them using RISC-V. A lot of people are focusing on either the microarchitecture optimizations or the firmware interfaces for RISC-V. I, however, fell in love with the architecture because of the core that keeps it all together, the instruction set. There are not a lot of RISC-V instructions, but they're all so well engineered. But some of them are cooler than others. You've already read the title. Let's rank all of the RISC-V instructions from S tier to F tier. Anyone familiar with RISC-V will immediately notice that this video is way too short to fit literally every single standard instruction. Yes, just now I said there are not a lot of RISC-V instructions, but once you get into stuff like the cryptography and vector extensions, that's not really true. There are a lot of vector instructions. The specification in the 2024 edition has grown to over 600 pages. That's about 3 times as large as the previous one. So what I've done is limited myself to the base architecture as well as the most commonly used extensions. This is the G extension group, as well as some subjective choices I made. I'm mostly using the order from the specifications instruction listing, so there should be no dramatic bias. Let's go! Ah yes, the base instruction set. This is the one I mean when I say RISC-V has very few instructions, because there are only 40 instructions here. What better place to start than the very first instruction from the 32-bit base instruction set? Load upper immediate is rather self-explanatory. It loads a 20-bit immediate into the upper bits of the 32-bit target register. The interesting part is how RISC-V encodes this and other instructions. All instructions are 32 bits, and the encoding includes operands in those 32 bits. Therefore, we can't really have an instruction for a 32-bit immediate load. Obviously, there's not enough space for a 32-bit immediate in a 32-bit instruction. The solution to this problem is very clever. Instead of loading the full 32-bit value in one go, what if we instead loaded the upper part of it with this LUI instruction? The encoding reserves 20 bits of space for an immediate. Then we add the remaining lower 12 bits onto this value by means of an add immediate instruction. Every 32-bit immediate load becomes 2 instructions. But more instructions does not automatically mean more bad in RISC land. In fact, it almost never means more bad. So LUI is there to perform the first part of the load. It's one of 3 instructions that reserve an absolutely massive part of the encoding space for 20-bit immediates, and for a very good reason, of course. While 12-bit immediates are enough for some purposes, 32-bit immediates are enough for basically anything, including on 64-bit systems. A tier for LUI. If you thought LUI had a funny name, you clearly haven't met AUIPC yet, add upper immediate to program counter. Once again, once we actually know what the acronym means, it's easy to figure out what it does. We take the same 20-bit upper immediate as in LUI, but instead of loading it directly into the register, we add it to the value of the program counter, i.e. the address of the AUIPC instruction itself. Now the obvious question is, what the fuck? Who needs that? Why do I care about the program counter if I'm not doing a jump? I can't even write to the program counter with this. Well, there's one obvious thing we can do with this instruction, which is simply reading the current program counter. Sometimes I guess that's useful, but in theory this is also possible by doing a jump. But that's not really the point of AUIPC. The point is really to load code offset addresses. What I mean is that a lot of program data, be it the global offset table of function pointers, function's address we want to call, some static variable, and many, many more. They all have a fixed position, at least relative to the code that we're currently executing. Obviously, all code is fixed relative to all other code, otherwise it would be pretty damn hard to run it. But even static data segments like .data and .bss usually have fixed positions somewhat close to the code. What AUIPC allows us to do is load a constant address like that by loading its fairly small offset from the current instruction address and, of course, adding another 12-bit offset with a secondary instruction if necessary. As we'll see later, adding this offset is also possible with a load or store directly, so if we're performing a memory access, we also only need 2 instructions. So AUIPC is super useful, as you can tell. In fact, you'll see any RISC-V disassembly littered with AUIPC instructions. But it's not just useful, no, this is where AUIPC earns its S tier. It makes position-independent code trivial. Let's learn about something fun called address space layout randomization. For security reasons, we really want our programs to never be located at the same place in memory twice. We want the address to be random each time the program runs. This is what ASLR does. It's something our operating system handles automatically. However, for ASLR to work, all the code in our program needs to be independent of the position that it gets loaded at. Absolute addresses can be used, but they have to be fixed by our operating system's dynamic linker right when our program starts. These dynamic relocations make programs larger and slower to start. Getting back on topic, with AUIPC, RISC-V inherently uses addressing relative to the current instruction, which means it's automatically position independent. No relocations, no complicated linker logic, no nothing. How amazing! S tier for AUIPC. Okay, I have to speed this up, but we also have to talk about how jumps work in RISC-V. First of all jumps are relative, and since JAL also uses that 20-bit immediate, with a bit of math we can calculate the jump range to be plus or minus 524 kilobytes in either direction. Almost correct. Since all instructions are at least 16 bits large, we don't need to specify the lowest bit. It will always be 0. So we double the range to about 1 megabyte in either direction. That's quite a lot of code. If we're lucky, any function we call will be within that range. This was the boring part of jumps, and all of them work this way, though with different ranges. The interesting part is the and link part of jump and link. What are we linking? The return address. All unconditional jumps store the address of the next instruction into the destination register, and only then jump to the new address. You might be familiar with how many architectures push the address of the next instruction to the stack once they perform a function call. But RISC-V never does this automatically. If we store the return address in a known register, the function we just called knows that this register must be retained for the return later on, so it can store it on the stack if needed. But if the function never calls another function, then it doesn't even need to do that. Neat optimizations all around. Of course, some jumps are just within a function and don't care about the return address. That's also very easy. We can store the return address into the 0 register, which by definition throws away all data and always reads back as 0. Overall, JAL goes into S tier, just for the reason of it implementing both function calls as well as an unconditional jump within a function. We just used JAL to make a function call. How do we return from the function? Easy, with jump and link register. This time the destination is not an immediate offset. It's instead an address stored in a register plus a 12-bit offset. You all know where this is going. Since we stored the return address in a register, all we need to do to return is to jump and link register with that same register. JALR can also do things like jump tables and any other application where you need a calculation to figure out your destination address. Overall, while it still has multi-purpose application like JAL, I'm only going to give it A tier for its slightly lowered usefulness. It's mostly just used for function returns. Okay, so I spend a lot of time on what, like 4 instructions? Fortunately, there is absolutely no need to talk separately about the next 6 instructions, all of which do essentially the same thing. The branch instructions. Branching, of course, means to jump only when a condition is met, and the conditions we can use are self-explanatory. Equals, not equals, less than, greater equals, less than with unsigned integers, and greater equals with unsigned integers. Now, you might actually not be surprised to see branching instructions like these if you've never seen any instructions of any instruction set. They're quite obvious and logical. We take 2 registers, compare their values according to the conditions, and then jump, or not, depending on the condition. However, this behavior is quite unique in RISC-V. Virtually all other instruction sets, even ARM, use flag registers to store the result of a comparison and then branch later on based on that previous comparison. But flag registers create several problems that are out of the scope of this video. You'll have to believe me that having no flags in our process is a good thing and another reason to like RISC-V. Anyways, no flags means that the comparison, of course, has to be part of the branch. And it also means S tier for the branch instructions. Let's increase the batch size to 7. Loading and storing to and from memory is one of the most basic things a processor does, so it's interesting that RISC-V pretty much has only these few instructions to do that. All of them do a different size, 8 bits, 16 bits or 32 bits, and some can turn off the sign extension, which is neat. All of them address memory via a register plus a constant offset, which is useful for object field accesses and getting to any 32-bit offset together with AUIPC, for instance. But if you have ever seen any CISC instruction set, you might be surprised that no other instruction accesses memory. This is because RISC-V is a so-called load-store architecture, just like ARM. There are instructions for loading and storing values, these 7, and there are instructions for doing calculations on the values, which we'll see later. And the 2 kinds of instructions do not intersect. There is no way of both loading a value from memory and also adding it to a value in a register in the same instruction. Load-store architectures are quite neat, but people have known that they're useful for a long time now. Lots of architectures do what RISC-V does here. It's neither unique nor mind-blowing. Still useful though. B tier. Do you still remember LUI and AUIPC? Well, here finally comes the instruction that we need for adding the lower 12 bits to that register. Or any immediate to any register, really. This is the perfect time to mention that RISC-V almost never overrides one of the source registers with a result. In this case, we can take a value from a register and add the immediate to it, but store that into a different register. Very useful if we need the original later. ADDI on its own would only deserve B tier, but it needs to be bumped up for one simple reason. What happens if you add any register to any immediate and store it in the 0 register? Exactly, nothing. It's a no-op. So naturally, we don't need a separate encoding for NOP, as we can just use any of the literal thousands of ADDI instructions that don't do anything. For complicated practical reasons, we only use one of them. But still, even useless instructions are useful in RISC-V, A tier. I had some trouble deciding what to do with those 2. Set less than immediate is intuitive in what it does, but a bit mysterious in its purpose if you ask me. It compares the register operand to the immediate and sets the result to 1 if the register was less than the immediate and 0 otherwise. Same thing with unsigned comparison in SLTIU, of course. This appears to be useful for comparisons for other purposes than branches, including, for example, composing comparisons into complicated conditions before actually branching, but it still feels evasive to me. I found it somewhat hard to read assembly code containing SLTI and SLTIU, but since there's a lot of that, they're clearly useful for compilers. D tier for the missing or poorly explained rationale. If you already know the instruction list, hold up. There is a reason why I am splitting XORI from the other 2. Again, on the surface, this is just the instruction for bitwise exclusive OR, XOR, between an immediate and a register, really nothing special. However, since the 12-bit immediate is sign extended, this means that we can easily XOR a register with all ones by just using the immediate hexadecimal FFF. And if you know anything about XOR, you know that this will flip all of the bits of the operand. A logical knot. Absolutely no need to use a separate instruction here. A tier for XORI. ORI and ANDI aren't special, as you may imagine. Simply a bitwise AND or with a 12-bit immediate. That part is quite limiting. They are still useful, don't get me wrong, but not much in comparison. C tier. Last of the immediate instructions, shifts. Of course, they're pretty darn useful. I would estimate that most shift amounts are constant and 12 bits is more than enough for the 6 bits we need for even a 64-bit shift. What's also quite neat is that some of the extra 6 bits of available space is used to differentiate between logical and arithmetic right shift. Solid A tier. I'm pretty sure I can hear quite a few of you shouting for a while now, through the screen. Yes, that really works. Where's the add instruction? Here it is. As I've said before, register-register instructions in RISC-V always use 3 registers, 2 operands and 1 destination, which makes a lot of operations easier without requiring additional moves. Additionally, sub serves as a negation instruction since we can just subtract any register from the 0 register. Even so, these instructions are pretty boring and basic, so they get B tier. From now on, the instruction listing order gets kind of weird, so we have the logical shift left instruction all on its own over here. I gave the immediate shift instructions A tier for the usefulness of constant shift offsets, and equally, I think the register-register versions are a little less important, so they belong in B tier. Once again, here are the set less than instructions, now as register-register versions. Still D tier, even if they are more useful than the immediate versions. As we saw previously, XORI is more useful than it may seem. That is not true for XOR, it's just as useful as an XOR operation is in general. So not a lot, but also not useless. C tier. As I said, register-register shifts belong in B tier. The 2 remaining logical instructions go to C tier like their immediate counterparts. We're almost at the end of the base instruction set, and FENCE is the first instruction relating to system operations that we can do in normal applications. As the name implies, FENCE is responsible for memory fences. Most of you probably aren't fully aware of what that means, so let's try getting an idea of some of the most complicated things in the RISC-V ISA. Memory models. The memory model is the formalized model of the order of loads and stores issued from a certain processor and how that order is observed by all other processors. It is most relevant for any multiprocessor system with complex memory mapped I/O, where there is multiple devices accessing memory at the same time with possibly unpredictable timing between them. RISC-V has almost 100 pages and 3 chapters in the specification dedicated just to the memory model. So forgive me for giving a really fucking simplified explanation here. Very important, the memory access order can be observed differently from different processors, and multiple different orders are all allowed. This allows a processor to use caching and out-of-order execution to run code faster. However, this also means that some really surprising things can happen, like certain addresses in memory yielding different results for different processors, and non-determinism in general. The more this can happen, the weaker the memory model is, but the faster the processor can theoretically be. Looking at x86, it uses a fairly strong memory model called total store ordering, which basically requires that all stores performed by a processor always appear in the program order. But processors can still load outdated values if they haven't seen a store yet. While TSO is not the strongest memory model, that would be sequential consistency, RISC-V uses a far weaker memory model that's almost like release consistency. In this model, the rules mainly say what order the accesses to the same memory location by the same processor have to appear in. Obviously, it's the same order as the program itself. But for unrelated memory locations, basically anything goes. Sometimes this creates problems. In complex synchronization situations, we may be dealing with more than one shared memory location. Here's where we finally get back to our topic. Fences allow us to limit reordering of loads and stores across them. The instructions literally cannot jump over the fence. There are several options for what accesses we want to limit and in which direction, which will give us things like acquire or release fences. FENCE.TSO is a special case that will give us exactly total store ordering across this fence, which can be used to emulate total store ordering for compatibility with x86 software. Overall, these instructions deserve A tier because the RISC-V weak memory model makes it super easy to create fast hardware while not making concurrent programming too complex to think about. Okay, that memory model section was probably a lot to take in. Let's relax and get deeper into system software. Obviously, most software running on a system has some level of software below it. Below the application is the operating system. Below the operating system is the firmware. Below the firmware is the Intel Management Engine. Just kidding, no IME on RISC-V. Yet. Some functionality is not immediately accessible to us, like opening a file or talking to the network. So, we need to ask the software below us to do it. When going from applications to the operating system, we call this a system call. This even goes for operating systems, which need to ask the firmware to do certain low-level tasks from time to time, even if it's mostly necessary during boot and not so much later on. RISC-V provides a unified way of calling into the execution environment by means of the environment call instruction. This is actually quite unique. I don't know of any other ISA that uses a single instruction for all of its different environment calls. How we actually pass data between the upper and lower levels is up to our software stack. So ECALL is both very simple and very powerful. Immediate A tier for this obviously great design. The next instruction, however, is a different story. I once again really don't understand why it exists. I mean, it does have a purpose, debugger breakpoints. EBREAK is nothing more than a hardware breakpoint that returns execution to the debugger. Maybe I'm too stupid to understand how hardware debugging is implemented, and maybe I should read the RISC-V debugging specification. But I don't understand why this cannot be encoded in one of the many available knobs and needs its own special trapping instruction. C tier, I guess. What we saw before is all valid for 32-bit and 64-bit RISC-V. But when going to 64 bits, some extra operations are required, which we'll cover here. LD and SD allow us to load and store 64-bit values, which is obviously only necessary for 64-bit register widths. Equally, LWU provides unsigned 32-bit load to avoid the sign extension from LW on 64-bit, pretty obvious. Again, there's nothing special here, just necessary instructions that make sense. C tier. All the normal integer operations use the full register size, so 64-bit for RV64. But operations on 32-bit values are still super common, and when we consider overflows and sign extension, the semantics are different enough that 32-bit arithmetic would quickly become complicated on 64-bit. Therefore, all the relevant integer operations get a 32-bit variant that retains the 32-bit semantics. Very useful, unfortunately a bit boring. C tier again. We're finally done with the base ISA and continue with some smaller extensions outside of the G listing before continuing later on. The CI hint pause extension defines a simple pause instruction, which previously was a no-op fence. However, now it becomes a basic waiting instruction that tells the system that we're waiting on some condition to become true, like some memory written by another processor or an external device operation. While we could make such waiting super precise, telling the processor exactly what we're waiting on and for how long, in many cases this simple pause instruction is enough. There are several optimizations possible with pauses. We could slow down the processor for some period of time after each pause. We could even stop it temporarily. We could execute some other code instead. All neat things that will increase efficiency or power consumption. However, since this instruction is limited even compared to something like wait for interrupt in ARM, I don't regard it super highly. D tier. Let's get back to memory models for a second. As you will have noticed, the previous fences were all about data accesses, loads and stores. But what about instructions, which also need to be read from memory? So far, there is no way of assuring that when we write entirely new code to memory, after a certain point, all instruction fetches will definitely see that new code. Therefore, FENCE.I exists as an instruction memory fence, which does exactly that. It's a very specific thing, useful for low-level paging code and just-in-time compilers, and it's not super special, but I think it deserves a solid B tier. Conditional instructions are quite common across instruction sets, and they are very appealing. We can skip a single instruction depending on a condition, avoiding branches and their large overhead. RISC-V once again found the best way of implementing this by only providing the simplest possible conditional instruction. If condition is equal 0, copy 0 to the destination, otherwise copy source register to the destination. That's the behavior of CZERO.EQZ, and CZERO.NEZ just flips the condition to not equal 0. Then it's really easy to implement most common conditional operations in 2 instructions and the rest in 3 instructions. I have to be honest, when I started researching these relatively new conditional instructions, I was skeptical, expecting the horrors of x86 and even ARM to creep in. But luckily, this is probably the best combination of elegant and powerful they could have found as a solution to this problem. A tier. Okay, so the future extensions are going to get very complicated. There are going to be a lot of configurations we'll have to choose, errors being reported, and hardware information we'll want to read. This is what control and status registers, CSRs, are for, and there are 6 basic instructions for interacting with them directly. All CSR instructions are atomic read, modify, write, which is important as some of them are shared between cores. The read-write instructions write the source into the CSR and read the old CSR value into the destination. The set instructions set the bit from the source, while the clear instructions clear those bits. Both of those are more useful than they sound, since many CSRs contain multiple bit flags and we usually only need to change one or a few of them. There are also the immediate instruction versions, which are useful too, since most data lives in the lowest 12 bits of any given CSR register. Overall, given how well designed the CSR system is and how many different important functions it performs across the system, I have to give these instructions a solid A tier. I'm going to give you 2 seconds to think about this. Which fundamental arithmetic operations are missing from the base integer instruction set? Pretty obvious, hopefully. Integer, multiply and divide. There is an equally obvious reason why those are not in the base instruction set. Implementing multiplication and division in hardware is extremely expensive, so it's part of a separate extension. These are the basic multiplication instructions, so you'd expect me not to have much to say, but that's not the case. After all, a 64 by 64-bit multiplication can yield a result up to 128 bits, but we only have a single destination operand? This is where all the high instructions come in, which give us the upper half of the result. They come in 3 variants for doing a signed-signed, signed-unsigned, or unsigned-unsigned multiplication. In case you're wondering, math tells us that for the lower half of the result, signed or unsigned does not matter, so we don't need these variants here. 2 instructions for 1 multiplication sounds kind of expensive, but if we put these instructions right next to each other, it's pretty easy for advanced processors to only do the multiplication once and use the result twice. Overall, super well designed and useful. A tier. Division and remainder are a bit simpler, as their results always fit in one register, and the only variant necessary is an unsigned variant. Once again, subsequent division and remainder instructions can be fused to only perform the division once. However, it's quite interesting what happens if we do the infamous divide by 0. Many architectures raise an exception here. RISC-V does not and produces well-defined values that match the most common hardware implementation behaviors. What a genius move! And not causing hardware exceptions makes things infinitely less complex. A tier. Once again, when we're on 64-bit, we need some way of doing 32-bit arithmetic, so these instructions exist to help us. Same story as before, C tier for necessary but boring features. Did you think that memory models would not come back to haunt us again? Funny. Let's talk about atomic operations, operations suited to multiprocessor synchronization. So, sometimes we have simple atomic operations, just the read, modify, write without being interrupted. However, those are really not suited for more complex operations where we need more than just a single atomic to ensure processes are synchronized. There are many different solutions for this problem, and RISC-V chose one that I think is somewhat unique while still turning out incredibly useful: the load reserved and store conditional pair. First, we execute a load reserved, which is a normal memory load, but also makes a reservation on the address we just loaded from. Then, sometime later on, we can execute a store conditional, which seems like a normal memory store, but is actually special. If the store conditional is to the same address as the last load reserve, and no other processor has written to that address in the meantime, it succeeds and performs the store and writes 0 to the destination register. Otherwise, it fails and does not store to memory and writes non-zero to the destination register. This means that we can do a read, modify, write with any complex operation we want, and we can check if anyone else modified the memory location in question while the operation was still ongoing. In that case, of course, we have to retry the operation. I hope it's obvious how many synchronization problems we can solve very well with these instructions. The standard example is the all-important compare and swap operation, which takes only 4 instructions in line. But there are many other applications for this brilliant instruction pair. S tier. In most cases though, LRSC and manual read, modify, write is way too complicated. We just want all of it to be done in one instruction with guaranteed success. This is what the other atomic memory operation instructions are for. They just do some calculation with the memory value and the second operand, store the result back in memory, and return the old value in the destination, all in one go. For example, with AMO add, we can do a very easy parallel sum reduction atomically in memory. Overall, while these instructions are not mind-blowing like LRSC, they are still quite useful. B tier. These 4 work the same way as the other AMO instructions, but I find them to be quite a bit more interesting since they do maximum and minimum operations, which seems to me more useful in some cases and more unique than the others. That's why I'm bumping them up to A tier. Okay, this was a long time coming. floating point. The instruction count is going to almost double because there are just so many operations with floats. I'll be breaking with my previous rule and group these instructions a bit more sensibly, since a lot of them do almost the same thing but are still listed in completely different parts of the table. And I'm covering both single and double precision floating point at the same time. Starting simple, we have memory loads and stores for floating point values. This is really nothing special. As you'll see, the float instructions are just like the integer instructions with their load store architecture. C tier for being a basic bitch. Basic floating point operations are as you would expect them, and they're very similar to integer operations in all regards. There are no exceptions when we divide by 0 or otherwise produce an NaN. There is just a flag set in the floating point exception CSR. Very interesting is that the rounding mode can be set directly in almost every instruction, and we can also set it in a CSR as a dynamic rounding mode. Some of these rounding modes are not even supported by x86. Definite A tier for the design here. Now we come to a very controversial part of the instruction set: fused multiply add. The problem with these instructions is not that fused multiply add is not useful. It is in fact very useful for lots of math, especially linear algebra. The problem is more that these instructions need 3 source operands, which takes up a massive amount of instruction encoding space. I have seen quite a bit of arguing that this is very much not worth it, that these instructions should have rather been used for vector instructions with dedicated masks and the likes. But when reading assembly code, it is notable how much these instructions are indeed used in practice for basically everything in floating point math, so they seem to be really worth it. I'm still giving them B tier overall. Yes, we only have a single advanced math function as an instruction, the square root. Not sure why exactly, there is a lot of space for others. It's useful, don't get me wrong, but it's so alone. C tier. So what about signs? What about negation, sign extraction, absolute values, and so on? The 3 sign injection instructions solve these problems by literally injecting a sign from one operand into another operand. And fsynjing can also invert the sign, giving us negation. And fsynjix will XOR the 2 signs together, giving us absolute value. And if we inject the sign of a number into itself, we get a move. As simple as that. These are absolutely genius instructions for many different common and uncommon floating point operations. S tier. Next, some boring instructions, just floating point equality operators. They're not branches, but only write the result of their comparison into the destination integer register, so we can use a branch equals to branch on them easily. Overall, not very special, but useful. B tier. If you're aware of the horrors that is IEEE 754 floating point, you're probably aware of the many kinds of numbers that it contains. Nans, infinities, normal and subnormal numbers, positive and negative 0. Floating point classify instruction allows us to distinguish the 10 defined classes of floating point values. This is a very normal thing and probably required for the standard, so no bonus points. C tier for IEEE 754 fuckery. If you read the instruction listing, this one takes up the most space, but really it's only one kind of instruction, the floating point conversions. You can convert from an integer to a float, from a float to an integer, and from single to double precision and back. Nothing special about that, basic necessary instructions that cover all cases, including unsigned integers. B tier. Finally, something that's actually a bit special. Float integer move. You might be saying, wait, that's the exact same as the float integer conversion instruction, but nope. Move means a verbatim transfer of the exact bits from the integer register to the floating point register, or the other way around. This is super convenient, especially when we consider that there's no float immediate instructions, So making a floating point immediate on the fly would otherwise be quite complicated and involve a memory load. However, with the move instructions, we can construct the constant in the integer register and then transfer it over. If the constant is simple enough with a mantissa that's mostly zeros in the least significant places, it might be enough to use one Louis in an fmove.x.s to construct a single precision float in 2 instructions. Funnily enough, even the super complex x86 instruction set doesn't contain this kind of move, not in x87, and as far as I can tell, not in SSE or AVX either. They always have to go through memory for this kind of operation. Anyways, that's a straight A tier for fmove. And here we are, all instructions from RISC-V in one large tier list. A lot of high tiers, and even that's relative. Most instructions here are far better than what's provided in other popular architectures. If you made it until the end, I taught you almost everything important about the most common instructions, and you will be able to understand some RISC-V assembly code. Well, okay, I guess we didn't discuss pseudo instructions all that much, which occasionally look weird but make your life a lot easier when programming. I hope you enjoyed this list and that you're now as excited as I am for RISC-V with its power and flexibility. Until next time.